Dizzying Oscillations, Part A, a lecture on simple harmonic motion. We're going to learn about springs and pendula in this lecture, and those will be the basic oscillations, simple harmonic motions or simple harmonic oscillations, that we'll study. But many types of oscillations can be approximated as if they're made up of the oscillations of springs or pendulum. Here we see balls on springs connected in a solid structure. This is actually representing, the balls represent atoms or molecules, and the springs represent the electrical bonds between them. It turns out atoms and molecules, how they interact when they get bonded together by the electrical attractions and repulsions, makes them oscillate back and forth as if they're hard spheres. The atoms are hard spheres, or molecules are hard spheres, oscillating back and forth from the electrical attraction and repulsion as if they're hard spheres on springs. So all liquids and gases, and all solids and liquids and gases that at high temperatures can vibrate, can be modeled as if they're balls on springs. So learning about the oscillatory motion of springs is ubiquitous because it also helps us learn about the vibrations and oscillations of solids, liquids, and gases of all matter. So if the atoms and the molecule do not move too far under ordinary temperatures and pressures, the force between them can be modeled as if there were springs between the atoms. The potential energy acts similar to that of a simple harmonic oscillator. A review of energy conservation. What you're looking at is a plot of energy conservation, an old plot that we've seen before, where the total energy is kinetic energy and potential energy of a spring. Recall the equations for kinetic energy and potential energy of a spring. The potential energy of a spring depends on the displacement of the spring from equilibrium. The total energy can be found by knowing the maximum displacement, and therefore the maximum potential energy of a spring, when all the energy is potential and none is kinetic. Or, when the displacement is zero, all the potential energy goes into kinetic energy, and the kinetic energy maximum, therefore, is the total energy. Here we see A through I images of a mass on a spring as it's oscillating. It's a motion diagram, in a sense, of a mass oscillating on a spring, from its lowest point to its highest point. At which of the above times is the displacement zero? Well, the dotted line indicates the equilibrium position of the mass spring. The displacement is zero at the locations when the mass is at the equilibrium, by definition, and that is A and E. At which of the above times is the velocity zero? Well, that's when the mass is at its maximum displacement, or its amplitude, and that's at C and G. Which of the above times is the acceleration zero? Well, if there's acceleration, there has to be a net force. Acceleration means the speed would be increasing or decreasing, and a net force on the object, which can only be from the spring, a force of spring would be present. Well, when is the acceleration zero and the net force zero? When the force of the spring is zero, at A, E, and I, at the equilibriums. At the equilibrium positions, it is neither speeding up or slowing down, hence its acceleration is zero, and there's no net force of the spring, hence it's at equilibrium. At which of the above times is the kinetic energy a maximum? Well, the kinetic energy is a maximum when the speed is a maximum. So when is the speed maximum? It's at equilibrium. Anytime it's past equilibrium, where there's a displacement of the spring, the mass is slowing down. The mass is always slowing as it's going away from equilibrium, or gaining speed towards equilibrium. The maximum speed it can have, and therefore the maximum kinetic energy, is at equilibrium. It's also where the potential energy is a minimum, so it must be the location of maximum kinetic energy. Which of the above times is the potential energy a maximum? Well, at the displacement, C and G again. Which of the above times is the kinetic energy being transformed to potential energy? The potential energy is going to kinetic energy when the object is gaining speed, when the spring is relaxing. The kinetic energy being transformed to potential energy. The kinetic energy being transferred means it's slowing down. The energy is going into, the potential energy is going into the spring. The object is slowing down as the spring is being stretched. Energy is going into potential energy as the spring is being stretched. That's from A to C and E to G. At which of the above times is the potential energy being transformed to kinetic energy? This is the point when the spring is relaxing and the speed is increasing. And those are the other locations, from C to E. It's going towards equilibrium. And G to I, the spring is relaxing, it's going towards equilibrium. Hence, the potential energy of the spring is going towards kinetic energy. Let's learn the vocabulary for oscillators. Period is the time for one complete cycle of an oscillation. You've used this before when we talked about the period of the ball and a string. Whipping a ball and a string on an object in circular motion takes one period of time to complete one revolution or one cycle. So period is simply short for the period of time for one complete cycle or one complete oscillation or revolution. The frequency is the inverse, the number of complete cycles per second. It's 1 over the period. The longer the period of time, the less frequently something happens. The more frequently the oscillation, the shorter period of time it takes. Angular frequency is 2 pi times the frequency, represented by omega. It is the same omega we've been using, delta theta over delta t, the angle over time. When delta theta is equal to 2 pi, one full oscillation or revolution, the time is one period. So 2 pi over one period would be omega for one full oscillation. But 2 pi over the period is the same thing as the frequency. So 2 pi over the period is the same thing as 2 pi equals the frequency, 2 pi times the frequency. So omega is 2 pi times the frequency, or 2 pi over the period, just as before. Amplitude is the maximum displacement from equilibrium. The full stretch of a spring or the full compression of a spring. The maximum angular displacement of a pendulum would be the amplitudes. Negative and positive amplitude aren't distinguished except by direction. What do we mean when we say an oscillation? That's a cycle. Any repeating motion is an oscillation, such as you commute to work and home, and then from home to work and work to home and home to work, etc. That's a repeating motion, an oscillation. Or the swinging back and forth of a pendulum is like the swinging back and forth of a dog's tail. It's a repeating motion. If the repeating motion recurs at regular intervals, a regular repeating motion, we call that a harmonic motion, such as commuting at the same time every day, from work to home, work to home, work to home, from 9 to 5, 9 to 5, 9 to 5. It's the same repeating regular oscillation. That would be a harmonic oscillation. If you work 7 days a week from 9 to 5, it's a harmonic oscillation, a regular repeating motion. Of course, we take off on the weekends, and so it wouldn't be a harmonic oscillation. Or if you work from 9 to 5, and then 8 to 6, and then 12 to 10, that would not be a regular repeat, a regular interval. That would just be an oscillation, not a harmonic oscillation. If the dog's tail wags back and forth the same way over and over and over again, exactly the same repeat of the motion, that would be a harmonic oscillation. Harmonic comes from Pythagoras, or the Pythagorean cult, who was interested in the oscillations involved with music. When a string vibrates, say at 440 times a second, or 440 hertz, we hear that vibration as something pretty, an A note. That regular repeat of 440 hertz being the frequency 440 times per second, that's a harmonic oscillation, a regular repeating motion 440 times a second. Our brain interprets that for motions of strings and air, sometimes as notes and pretty sounds. What do we mean by a simple harmonic oscillation, or an SHO? Is a repeating in a certain well-behaved way that can be described by a sine function. So if the tail moves like a pendulum, fastest when crossing the axis of the body when it's at its lowest point, and slows down on its way up to the amplitude, where it's slowest, speed is instantaneously 0, and then swings back down to the lowest point where the speed is maximum, swings back up to the other amplitude, the other maximum angular displacement, the speed is instantaneously 0. That increase in speed and decrease in speed over and over again can be described by a sine function. Or the commute to work If you increase your speed and decrease your speed, increasing your speed and then slowing down, increasing your speed and then slowing down, the same way the slope of a sine wave increases and decreases, it would be a simple harmonic motion or simple harmonic oscillation. But of course it's not. You have to go through stoplights and traffic signs, etc. So most things aren't simple harmonic oscillations. Most things don't have oscillations that would map out on a position versus time graph as a sine wave. But many things can be approximated as. For example, when stars at their end of their lives, massive stars start throbbing. They change their size. Sometimes they throw away their outer atmosphere, sometimes they explode. But before that point, they start changing their size. They become variable stars. A regular variable star is a Cepheid variable star. What you're seeing here is a plot of the increase and decrease of the magnitude, the luminosity, or the brightness of the star. The star gets bright very quickly and then slowly dims away, and then repeats bright and then slowly dies away over a period of less, in this case, of 5 days and 40 minutes. Is this an oscillation? It sure is. It's a repeating motion, increasing in brightness and slowly decreasing in brightness, and then repeating that again, increase in brightness, decreasing in brightness. Is it harmonic oscillation? Well, it's a regular repeating motion. It increases in brightness the same way every time, and it decreases in brightness the same way every time. So yes, it's a harmonic oscillation. We can think about like copying and pasting the image of the increase and decrease of the Cepheid variable. We're copying and pasting the period of its increase and decrease. Thus, it's a harmonic oscillation. Is it a simple harmonic oscillation? Simple harmonic oscillation is something that looks like a sine wave. It looks sort of like a sine wave, but the increase in brightness is not the same as the decrease. It's not symmetric like a sine wave. So, although it might be somewhat similar to a sine wave, it's not a sine wave oscillation. So therefore, it's not a simple harmonic oscillation. Here we're looking at the voltage in EKG, the voltage of a heart over time. Is this an oscillation? Well, it's certainly a repeating motion. In fact, even in the graph, it shows there's a period of time between the increases in the voltages and the decreases of the voltages. The voltage is rapidly changing, but it's repeating. Is it a harmonic oscillation? Is it a regular repeating oscillation, repeating in the same way? Again, we can sort of copy and paste the period of motion over and over again and see we get pretty much the same regular repeat of the same oscillation. So yes, it's a harmonic oscillation. It may not be exact, but it's pretty darn close to being a regular repeat of the same oscillation. Your heart beats just about the same every single beat. Is it a simple harmonic oscillation? Well, it looks nothing like a sine wave. So no, it is not. We call the vibrations of a spring and the swinging of a pendulum simple harmonic motion, or hereafter SHM. It's the fundamental type of vibration. SHM is a sinusoidal, i.e. harmonic motion with a single frequency or a single period. Very few vibrations are purely SHM, but many are very well approximated. More complicated vibrations can be expressed as combinations of many simple harmonic oscillations. Another way of saying that is, we can model complicated oscillations as if they're made up of balls on springs where there's many types of springs that the connections are being made from. This is the oscillation of many types of springs, giving us complicated oscillations. Now on to the equations of oscillations. Whether it's a mass on a spring or a mass at the end of a string like a pendulum, the oscillations can be described with two formulas that you'll get familiar with. The frequency oscillation depends on the physical properties of the oscillator, the spring, and the length of the pendulum. It does not depend on the amplitude of the oscillation. The more you pull on a spring, or the more you compress a spring, won't change the frequency or the period of time it takes for a mass spring to vibrate back and forth. Increasing and decreasing the angle, hence the amplitude of a pendulum, won't significantly change the period of the pendulum to swing back and forth. You see here the equations that the frequency and the period of the pendulum and the spring depend on, directly taken from your textbook. The frequency of a spring we can make sense as, it depends on K, the spring constant, directly so. For greater spring constants, greater frequency, the greater the spring constant, the stronger the spring, the more tightly wound it is, and the greater frequency, the more frequently the spring would go back and forth. The greater the mass, the less the ratio, the less the frequency. The heavier the object that's on the spring, the less frequently it goes back and forth. The period is the opposite of the frequency. It's the inverse. The greater the mass, the longer period of time it takes. The greater the spring constant, the shorter period of time it takes. For a pendulum will swing back and forth more frequently depending on gravity. If gravity increases or decreases, the pendulum falls as it's swinging, so it would fall or swing at a greater rate more frequently or less frequently if gravity was increased or decreased. And in inverse, it depends on the length. A longer pendulum swings back and forth less frequently than a shorter pendulum. And the period also makes sense. The longer the pendulum, the longer period of time it takes to swing back and forth. Let's make sense of this. A series of pendulums is in the image below, A, B, C, D, and E, with different length strings and different masses. Each pendulum is pulled to the side, as shown, by the same small angle. The pendulums are released and they begin to swing from side to side. Rank the frequencies of the 5 pendulums from highest to lowest. Well, we know the frequency of a pendulum depends on the length and gravity. We assume all these pendulums, side by side, are also to the same gravitational acceleration. So there's no difference in gravity for these pendulums. The only thing the frequency of the period depends on is the length then. Mass does not come into play. Why? Because the mass on the pendulum is simply falling. It's being swung back and forth as it's trying to fall to the lowest point. But all masses are subject to the same gravitational acceleration. So mass doesn't come into play. Only thing we have to worry about is the length of the pendulum. So the shortest pendulum will swing back and forth the most frequently, and the longest pendulum will swing back and forth the least frequently. So A is equal to E, they're the same length. B is equal to D, less frequently than A equals to E, but more frequently than the longest pendulum C. It doesn't have to be a mass at the end of a length of a string, like a pendulum. It could be what's called a physical pendulum. A mass distributed, a real object, like in the second illustration, such as a limb, or a rod, or even a ruler. As those objects swing back and forth, they don't swing the same way as the center of mass, as a mass at the end of the string, or the center of mass acting like a point particle, a center of mass distance away. It has to do with moment of inertia. The way the mass is distributed relates to how easy or how difficult it is for gravity to swing a pendulum back and forth. The farther the mass is from the center of rotation, the greater the moment of inertia, the longer period of time, and the less frequently the object will swing back and forth. When mass is close to the pivot point, the moment of inertia is less, the object swings back and forth easier, and so the force of gravity and the gravitational acceleration on the object make a mass with smaller moment of inertia swing back and forth more frequently. The frequency equation for a physical pendulum, an object that has mass distributed along a length, is shown below. The key point is the moment of inertia determines how far the mass is from the pivot point. So the farther the mass is from the pivot point, the less frequently it swings back and forth. We can swing limbs back and forth, or bones back and forth, and see how frequently they swing back and forth, as they're simply released to swing back and forth, subject to the pull of gravity. We can do this for even bones of animals long extinct, such as a dinosaur, and figure out the period of motion it takes for a dinosaur's bones, such as the dinosaur leg, to swing back and forth. From that period of motion of the dinosaur legs to swing back and forth, we have an idea of the walking pace of a dinosaur. We can, of course, do the same thing with live creatures, swing the bones or the legs back and forth of live creatures, or creatures currently living, and compare it to the walking paces of live creatures, and see if this is a good approximation. And it is. Continue on to Part B, where we continue to develop the mathematics, the plots in particular, of oscillations and damping motion and resonance.